one of the closest massive stars to the Sun is acting weird. Betelgeuse recently dimmed down to just 1/3 of its usual brightness. What could be causing this irregular behavior? Could this mean that it's about to explode? Grab a cup of tea and settle in, because today we're going to be taking a deep dive into everything happening with the enigmatic Betelgeuse. Betelgeuse. Look up towards the Orion constellation and you'll find this infamous star at the shoulder of the mythological hunter. Also known as Alpha Orionis, it's easy to spot being the 10th brightest star in the sky. At least, usually, it's the 10th brightest. You see, over the last few months, astronomers have noticed something strange about this star. It's now about 1/3 as bright as usual, something noticeable by eye. In fact, it's now been demoted to the 24th brightest star. To understand what's happening, we first have to talk about some background about this star. Because you see, what makes this dimming particularly interesting is that Betelgeuse is no ordinary star. No, in fact, for example, it is far younger than our own Sun. Whilst the Sun was born from the gravitational collapse of an ancient giant molecular cloud some 4,600 million years ago, Betelgeuse was probably born just 10 million years ago. For some context, this would be about the time that our hominid ancestors started to splinter off from what would become gorillas. If we spread the Sun's age out over a calendar of 365 days, Betelgeuse would have been born on December 31st at 5 AM. It's so damn young that rocky planets like the Earth would likely not have had enough time to have formed yet, and frankly, likely never will. So Betelgeuse is a very young star. But in another sense, it's actually an old star, at least when we compare it to how long this star is expected to survive. So let's compare it to the Sun. The Sun can be thought of as middle-aged, enough fuel to last for another 5 billion years before eventually evolving into a short-lived giant phase, and then, finally, leaving behind a dead white dwarf. Betelgeuse, on the other hand, is running on empty, and it has in fact already transformed into its giant phase. You see, Betelgeuse has been very greedy during its short lifetime. It was born with a whopping 15 times more mass than our own Sun, and ever since it got going, it's just been feasting through its fuel supply like a bat out of hell. The star is a monster. It spews out 100,000 times more power than our own Sun does. And even before becoming a giant during its main sequence lifetime that the Sun currently enjoys, it still, even then, would have been spewing out tens of thousands of times more power than our own Sun. You've probably heard the expression, the candle that burns twice as hot lasts half as long. Well, here we'd say that the star that burns 10,000 times as bright lasts 1,000 times less long. Although, admittedly, we are talking about a star that began its life with at least 10 times as much candle wax in the first place. Massive stars like Betelgeuse are actually very rare. Just like animals, most develop into a fairly average size for their species, but rarely you get a freakish set of circumstances that somehow result in a giantized example, and these giants really stand out. In the same way, Betelgeuse is a freak because only 1 in 200 stars will be born with as much mass inside them as Betelgeuse was. And not only is Betelgeuse massive, the fact that it's entered its giant phase means it's also humongous. To understand this gargantuism, let's look inside a star. A star has 2 key zones: the core, where fusion happens, and the envelope, which is basically just hot gas sat on top. As stars fuse hydrogen into denser helium inside their cores, they accumulate an inert inner core of helium ash inside their centers. Now, because helium is denser than hydrogen, the core contracts, which in turn causes it to heat up. Eventually, the central temperature and pressure become extreme enough that helium can now fuse into carbon via the triple alpha process, which substantially increases the energy output of the core, and this in turn causes the outer envelope of non-fusing hydrogen to simply puff up, a bit like a hot air balloon. Except that that balloon has now puffed up to the size of Jupiter's orbit around the Sun, a gargantuan size. So this broadly describes what's happening inside Betelgeuse right now and why it is as big as it is. But it will not stay in this state forever, because as it's accumulating now carbon ash inside its core, the temperature and pressure will continue to rise in the center. Eventually, even the carbon and heavier elements still will be able to start fusing. And once this happens, well, the end is nigh for Betelgeuse. We'll be looking at a few hundred years, perhaps a couple of millennia, until its demise. What happens to massive stars like Betelgeuse when they die? There are 2 likely possibilities. The one you are probably hearing the most about is a supernova. Remember that the core will eventually start to fuse carbon and even heavier elements in its center. But once it starts producing iron ash, well, the gig is up. That's because fusing things heavier than iron is what we would call an endothermic reaction. And all that means is that you actually have to put in more energy to conduct the reaction than you get out the other end. In other words, this reaction saps energy from the core. Remember that this is a massive star, and so it has a huge self-gravity trying to collapse it in on itself. When the heat source starts to dwindle due to the accumulation of this iron ash, well, there's nothing to resist that gravitational collapse anymore. And so the star literally falls in on itself, imploding. It's at this point that the 2 possible futures for Betelgeuse diverge. One is going to be a bang and the other is a whimper. As this wave of infalling material, the outer envelope of the star falls in towards the core due to gravity, one of 2 things is going to happen. Either the core is going to structurally resist that infalling wave and it will just sort of bounce off the outside, or the core will not be able to resist and it will simply crush down. Stars on the lighter end of the massive star spectrum, around 10 times the Sun's mass, will not generate enough pressure to collapse the inner core. Instead, they'll merely compress it into a superdense neutron star state, and then bounce off that neutronic interior. That bounce back leads to a giant shockwave that propagates out into space, releasing tremendous waves of energy and spewing matter deep across the void. And that's what we call a supernova, or to be a little bit more technical, a core collapse supernova. But what if the star is heavier than 10 times the Sun's mass? Well, now there is a lot more material falling down onto that inner core. So much so that it can actually overwhelm even the resistive strength of neutronic matter. And so the star will fall in, crushing the core. In fact, it will fall all the way in, all the way in to a singular point of infinite density, a black hole. In some cases, the bounce back still happens, it forms a neutron star, but some of that wave of bouncing out material ends up falling back onto the neutron star, and it just tips the balance enough to turn that neutron star into a black hole all the same. But in other cases, there is so much infalling material that the star just literally implodes. It winks out of existence. There's no bounce back, there's no supernova, there's no bang of any kind. It just disappears. This winking out has in fact been seen before. Around 2010, astronomers witnessed another red supergiant in the galaxy NGC 6946 simply disappear. This actually wasn't even noticed at the time, and it was only later that a couple of astronomers at Ohio State University checked carefully through the archival data and found this remarkable event. Now, that star was likely born with around 25 times more mass than the Sun, as shown here, but lower mass red supergiants in the range of sort of 10 to 15 times the mass of the Sun have been seen to do the opposite and explode. Now, if we compare these observations to theoretical models, it matches up quite nicely. Here, you can see a prediction for whether the star will implode into a black hole, winking out, or turn into a supernova in green, and this clearly depends on the star's mass. The outcome of these models shows some randomness. The rotation speed, metallicity, and intrinsically stochastic nature of the star's interior means that we can't always predict exactly what will happen based on a star's mass alone. And so this is why, in part, it's so difficult to say exactly what will happen to Betelgeuse. This situation is exacerbated by the fact we actually don't know the mass of Betelgeuse, and certainly not the mass of Betelgeuse it was born with, very well. And that's because in turn we don't even know a precise distance for Betelgeuse. And so in turn this means that we end up with a very large uncertainty on its mass. So comparing to the theoretical models, one can see how it's certainly possible that Betelgeuse might just disappear one day, without a bang. Okay, so with this fascinating background about these massive stars out of the way, we can now finally talk about what has been happening with Betelgeuse over the last few months. The first thing to say is that Betelgeuse is a variable star. I mean, it is not surprising for its brightness to change. It's not a light bulb. Its brightness changes by a few percent, even 10% quite often, and that's been seen for decades now. What's really unusual about what's been happening lately is that this is a fairly constant and steep regular decline in brightness, which has gone really quite deep, down to 1/3 of its usual brightness, and that is frankly kind of weird. I want to emphasize that that number represents the minimum in the star's recent episode of dimming. In the last couple of weeks, it has actually started to stabilize and even reverse, brightening back up again. The story gets extra spicy when we throw in these two images of the star taken about a year apart. Now, normally it's impossible to resolve individual stars like this, but some supergiants are so big that we can at least get a fuzzy image like this one. Clearly, Betelgeuse looks quite different between these two photos, and that fact, combined with the dimming, has a lot of folks quite worried. So let's just ask the obvious question that's on everybody's lips right now, and that is, does this dimming of Betelgeuse mean that it's about to go supernova? Short answer, probably not. And there's a few reasons for this. First off, we really don't have any clear prediction that stars are expected to undergo a period of dimming before going supernova. The hydrodynamics of these stellar interiors is very complicated, and there's an intricate feedback with gravity waves that actually affects their luminosity output in a fairly unpredictable way. Here's an example of a prediction for the luminosity of a star, essentially how bright it is, versus its surface temperature in the final years before its death, from Professor Jim Fuller. The star's luminosity is indeed sometimes dimming, but it is also often brightening too. I mean, it's really all over the map. We've never really caught a supernova in the act before, at least in the days and years preceding the event, and so we can't really tell you from data how stars behave just before they go supernova. And so these models are really kind of the best we have right now. And so, frankly, we just don't know how stars behave just before going supernova. We don't know that it looks like what's happening right now. Now, in that model prediction I showed you for the star's pre-supernova behavior, what's being shown here is the luminosity. Now, it's tempting to say that this widely reported recent dimming translates directly to a decrease in luminosity, but that's actually not true. Now, these reported dimmings that we've been hearing about have all been of the star's brightness in the visible light part of the spectrum. But Betelgeuse, like all stars, produces radiation at all different wavelengths across the entire electromagnetic spectrum. And so if we want to calculate luminosity, we have to actually add up all of that brightness across the entire spectrum. And that's not what we observed with these dimmings. It is not the luminosity of the star. Fortunately, of course, there is a way that we can get the luminosity. We just simply have to do these observations at other parts of the spectrum apart from visible light. And that's exactly what astronomers have very recently done. Infrared measurements taken at the Orion Observatory in Minnesota just last week showed that the star has the same brightness in the infrared as it did 50 years ago. In other words, this dimming does not represent a change in the star's overall power output. It's just limited to the visible light part of the spectrum. Okay, so maybe we can take our fingers off the panic button. We don't seem to be in the regime of a wildly varying star like Jim Fuller predicted. But then how do we explain this pronounced visible light dimming, as well as the strange lopsided image that was recently captured? There are broadly two popular theories to explain what has been going on with Betelgeuse recently, if we are willing to discount the supernova hypothesis just for the moment. The first is a giant star spot. If we look at the sun, we see small sunspots quite often. These are regions where the sun's magnetic field lines temporarily come together in a way that inhibits convection of heat from the sun's interior up to its surface. Without that heat coming up to this part of the surface, well, that patch of the surface cools down. It gets to about half of its usual temperature, and that in turn means that it appears darker. This is very much analogous to how if you pull a piece of iron out of a fire, it will glow red initially, but then cool down and stop glowing. Now, a spot or collection of spots that is big enough to block out about 2/3 of the star's usual brightness would have to therefore block out about 2/3 of the star's surface, at least the hemisphere that we can see. If the other hemisphere is spot-free, then this means that in total, about 1/3 of the star's surface would have to be covered in spots. For the sun, spots certainly never get so big or so numerous as to block out anywhere near this much of the surface. Other giant stars have been recorded to do this in the past. For example, the orange giant HD 12545 in the constellation Triangulum has had its surface resolved with a spectral technique called Doppler imaging that clearly reveals spots covering about 1/4 of the surface. Not quite 1/3, but close enough to show us that this is at least a plausible explanation. Now, for the sun, spots come and go on a roughly 11-year cycle. And at the peak of this cycle, about 1% of the star's surface is covered in spots, which corresponds to a fairly marginal change in the luminosity of the star. It actually only increases by 0.07%. And so stars' luminosities are fairly robust to changes in their spot coverage. When we combine all these points together, we can kind of see how this spot hypothesis could work then for Betelgeuse. We can explain the fact that luminosity doesn't seem to be changing very much. We can explain the apparent dimming in the visible part of the spectrum. And we can also explain that lopsided image, all with a single hypothesis. Now on the Sun, recall that spots are caused by magnetic field lines impeding convection. These spots are about the size of the Earth typically. But if we zoom in, there's another effect at play. Here you can see a much finer grain effect. Each one of these little cells that you're looking at is about the size of Texas. What's amazing is that this is real data from DACUS, not a simulation of our Sun. And here you can cleanly resolve the surface at incredible detail. Each little bubble that you can see is the top of a convection cell and is usually called a granule. The variability you're seeing is usually called granulation, caused by the convection of hot plasma beneath the surface, a bit like a lava lamp. The size of these granulation cells is directly related to the strength of surface gravity on these stars. So for the Sun, these cells are the size of Texas, and the surface gravity is about 270 meters per second squared. That's something like 27, 28 times Earth gravity. But for Betelgeuse, because it's so puffed up, the surface gravity is really pathetic. It's just 0.003 meters per second squared, which is about 3,000 times less than the gravity I'm currently feeling here on Earth. It's really quite ridiculous. And so, because the gravity is so weak on the surface of Betelgeuse, then these granulation cells get really, really big. Betelgeuse doesn't like to do anything small. There's some beautiful computer simulations of the convection cell behavior for such stars that I'm showing you here. It reveals just how effervescent, lively, and bubbling the exterior envelope truly is. Now sadly, we can't resolve the surface of Betelgeuse as precisely as this with existing telescopes, so let's downgrade the animation to the sort of fuzziness that we'd see realistically. In watching this, you indeed see that granulation alone can produce very large dark features on the surface, as well as creating lopsided images in individual frames. So all in all, I'd say that a fairly extreme episode of this natural convection behavior could be an explanation for what has been happening recently with Betelgeuse. But I promised you two possible explanations, and the other one is equally compelling. Now, remember that I said that the surface gravity on Betelgeuse is pathetically weak, and so that might make you wonder, hey, if I was stood on the surface of Betelgeuse, could I jump off into space? Could I achieve escape velocity? The escape velocity is given by the following equation, where g is the surface gravity and r is the radius of the object. For the Sun, this gives about 600 kilometers per second. So you're going to need a lot of energy to ever leave the Sun's surface. On Betelgeuse though, it's about 10 times less, just 60 kilometers per second. And so this raises the possibility that a strong convulsion from within the star's interior could have propagated out to the surface with enough force to have actually flung off the outer layer into deep space, or at least a part of it. And once that layer was dispatched from the star, it would have cooled down and eventually ended up blocking out some of the star's light. Essentially, it's just dust. We even see some evidence for previous episodes of dust released, as you can see here in this real image. Now with the giant spot scenario, the surface has actually cooled a little bit, but here the surface is essentially the same temperature, it's just that there's some dust getting in the way. And so recent work by astronomer Emily Levesque investigated what the temperature of the surface was using a spectral technique. They found that the star's surface doesn't appear consistent with an episode of dramatic cooling, and so on this basis, they favor the dust hypothesis. And so this leaves us with two quite compelling explanations without the need to invoke a supernova. Now, because there's so much we don't know about how stars behave in those final years before turning into a supernova, then it is still absolutely possible that what we are seeing are the signs of an impending supernova. But typically, stars spend about 100,000 years in this phase of their life, and so it's just probabilistically unlikely that that will coincide with our short human lifetimes. It's also a shame, because if Betelgeuse did go supernova, it's 650 light years away, which means it's far enough away that it won't hurt us, but close enough that we would have the opportunity to study in great detail and learn so much about the final stages of this enigmatic type of star. Of course, it would also put up a very nice light show, outshining even the full moon at its peak brightness. Or it might just wink out, leaving behind a black hole, which would also be an incredible observation to see. Massive stars like Betelgeuse are amazing. Yes, they are unusual, rare beasts which are unlikely to ever form planets, let alone life, but on the other hand, they are also somehow intimately connected to us. That's because it's within these massive stellar engines that many of the heavy elements inside your body, things like phosphorus, potassium, oxygen, were forged deep within its interior. And when these stars came to their end, they violently exploded these enriched guts across the cosmos. Those newly forged heavy elements were cast out across the galaxy to distant shores. Because there was so much hydrogen left unfused, new, smaller stars formed from the debris, which in turn eventually formed planets enriched with these heavier elements crucial for life. And those same elements are inside your body right now. They were at one point in their history inside the bowels of one of the most massive stars in the universe. You are, in essence, made of ash. And so watching Betelgeuse is like getting to see one of the earliest steps in the origin of living things, like looking into a mirror of our own beginnings. These stars violently rip themselves apart in an almost sacrificial act, so that complex chemical entities such as ourselves might one day be born, rising like a phoenix from the flames.